This video is an easy visual proof of the Pythagorean theorem. Consider a right triangle with side lengths A less than B less than C, the hypotenuse, and angles capital A less than capital B less than C, which is 90 degrees. Angle A is opposite side A. Angle B is opposite side B. And opposite the hypotenuse C, the angle is 90 degrees. It's a right triangle. We'll show angle A with the color amber and angle B with the color blue. Amber equals A, blue equals B. The amber angle A plus the blue angle B equals 90 degrees because the angles of a triangle sum to 180 degrees and C is 90 degrees. The Pythagorean theorem states that lengths A squared plus B squared equals C squared for this right triangle. For each side of the triangle, the drawing also shows a square. The area of the red square is A squared. The area of the green square is B squared. The area of the gray square is C squared. The Pythagorean theorem says that the gray square area is equal to the sum of the red square area and the green square area. Let's do something with the gray square to see if we can prove this. Let's clone a copy of the triangle and slide it to the left and upwards until it touches the side of the gray square. The side of the square is the same length, C, as the hypotenuse of the triangle, because that's the size we made the gray square. What next? Can we tell anything about the gray angle between the triangle's side A, here, and the side of the square, here, this angle? The angle adjacent to the triangle's blue angle, B. All corners of any square are 90 degrees, so that the gray angle must be 90 minus B, so it must equal the amber angle A, since A plus B equals 90 degrees. Let's clone another copy of the triangle, rotate it 90 degrees, counterclockwise, and slide it adjacent to the first cloned triangle and the side of the square. It fits perfectly. No gap. What next? Well, let's look at this angle, this gray angle. Similar to the previous step, let's clone a third copy of the triangle, rotate it 180 degrees counterclockwise, and slide it adjacent to the second triangle and the side of the square. It fits fine. So here we have B plus A is 90 degrees, and here we have B plus A is 90 degrees. And let's do a next step here. Here's angle B. Would a fourth clone of the triangle fit adjacent to the third cloned triangle and the side of the square and the first cloned triangle? Yes, each corner of the square is exactly covered by one amber angle A from one triangle and one blue angle B from another triangle. Everything fits perfectly. Here we have blue and amber making 90 degrees, blue and amber making 90 degrees, blue and amber making 90 degrees, and blue and amber making 90 degrees. What's next? The four triangles don't completely cover the gray square. A small square at the center is left over. What size is it? Looking at the triangles, we see that the sides of the small square have length B minus A. Now, the area of the large square, C square, equals the area of the four triangles, 4 times 1/2 AB, so that's 2AB, AB. 2AB is the area of the four triangles, plus the area of the small square. Well, the small square area is B minus A, squared. Now, if you do this algebra, you get A squared plus B squared. And that's the area of that will equal the area of the large square, so that's C squared. C squared equals 2AB plus B minus A squared, which is B squared minus 2AB plus A squared, which is A squared plus B squared. A squared plus B squared equals C squared. This is the Pythagorean theorem. We chose A less than B, and the four triangles didn't completely cover the gray square. If we had made A equal B, we would have found that the four triangles completely covered the large gray square, and there's no small square left over in the middle. Each triangle's area would have been 1/2 A squared, and the four together would have been 4 times that, or 2A squared, which would equal A squared plus B squared, since A equals B in that case, equals C squared. Now, instead of placing the triangles inside the large gray square, we could have placed them outside it, such that the large gray square plus 4 triangles exactly forms a new larger square with the sides of length A plus B. Maybe you can do this by yourself and use a little algebra as an alternate proof of the Pythagorean theorem. Changing direction, let's look at a special triangle. Suppose we draw a triangle with side lengths 3, 4, and 5. So 1, 2, 3, 1, 3, 4, and this is the triangle. Can we tell whether this is a right triangle or not? 3 square plus 4 square equals 9 plus 16 equals 25 equals 5 square. So this is a right triangle. Take a sheet of paper with a square corner, measure off 3 units horizontally from the corner and mark that point. Measure off 4 units vertically from the corner and mark that point. Measure the distance between the 2 points, and it will be 5 units. The 3, 4, 5 right triangle is easy to remember and can be useful for measuring whether a corner of a room is square 90 degrees. Now, what about a different triangle with side lengths 5, 12, and 13? Does that form a right triangle? You should find that it does. Integers that form a right triangle are called Pythagorean triples. The Pythagorean Theorem has been known for at least 2,300 years, and Pythagorean triples may have been known for 4,000 years. Our proof used algebra, but there are many different proofs of the Pythagorean Theorem that only use geometry. I hope you found this outline of a proof to be simple and memorable. Note that the Pythagorean Theorem applies only for right triangles in a plane. It does not apply for right triangles on a non-Euclidean surface, such as on a sphere. If you take a ball and you draw a large right triangle on a ball, and you measure the hypotenuse, you will find that the hypotenuse is not 5 units of length when the other 2 perpendicular legs are 3 and 4. The Pythagorean theorem applies to triangles in a plane, not on a ball.